Welcome to Virtual Learning Network. This e-lecture is on Computer Organization and Assembly Language Programming, Block 1, Unit 2, Part 1, that is Data Representation. The topics to be covered under this unit are Introduction, Data Representation, Number Systems, Decimal representation in computers, and at the end, summary. First is introduction. In this unit, we will describe various types of binary notations that are used in contemporary computers for storage and processing of data, and will reintroduce you to the number system concepts and decimal representation in computers. First is data representation. The basic nature of a computer is an information transformer. Thus, a computer must be able to take input, process it, and produce output. But how is the information represented in a computer? It is in the form of binary digits, popularly called bits. In computers, information is represented in digital form. Therefore, to represent characters in computer, we need codes. Some common character codes are SCHI, EBC, DIC, SCHI, etc. We need to represent numbers in binary and should be able to perform operations on these numbers. Now, our next topic is number system. Number system is used to represent information in quantitative form. Some of the common number systems are binary, octal, decimal, and hexadecimal. Number system is a set of symbols to form numbers. Numbers are expressed by a string of digit symbols. To determine the quantity that a number represents is determined by multiplying each digit by a power of base called radix represented by r and then forming the sum of all the digits. Now we will discuss some common number systems that are binary, octal, decimal and hexadecimal. First is decimal number system. Decimal number system has 10 digits represented by 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Any decimal number can be represented as a string of these digits, and since there are 10 decimal digits, therefore the base or radix of this system is 10. Some of the examples of decimal number system are 3.14 base 10, 534 base 10. Next is hexadecimal numbers. The hexadecimal system has 16 digits which are represented as 0 to 9 and A to F. For example, F2 base H or base 16. Next is binary numbers. In binary numbers, we have two digits 0 and 1, and they can also be represented as a string of these two digits called bits. The base of binary number system is 2. For example, 101010 is a valid binary number with base 2. Next is octal number. An octal system has 8 digits represented as 0, 1, 2, 3, 4, 5, 6, 7. For finding equivalent decimal number of an octal number, one has to find the quantity of the octal number, which is calculated by a specific process. Example of octal number is 23.4 base 8. Now, after discussing about the various number systems. Now the next topic is numbering conversion. One number system can be converted into another number system. For example, decimal numbers can be converted into corresponding octal numbers, binary numbers, and hexadecimal numbers. Similarly, octal numbers can be converted into binary numbers, and binaries number can be converted into octal number, and hexadecimal numbers can be converted into binary numbers, and binary numbers can be converted into hexadecimal number. Now we will see the process of converting one number system to another number system one by one. First is decimal to binary conversion. To convert a decimal number system to its corresponding binary number system, repeat division method is used. For example, if we take a number, say 27 base 10, that is decimal number, and we want to convert it into the corresponding binary number, then we will divide it with 2, that is the base of binary number. You can see here, if we divide 27 by 2, then the remainder will be 1 and the quotient will be 13. Now we will divide 13 by 2 in the next step and find out the another quotient and remainder. Then 6 will be divided by 2, the quotient will be 3 and the remainder will be 0. Then we will divide 3 by 2, then the quotient and remainder will be 1 and 1, and after it we will divide 1 by 2 and the quotient and remainder will be 0 and 1. Now we will write the remainder from bottom to top, that is 11011 base 2. So binary number for 27 base 10 is 110112. Another example you can see here, that is 181 base 10, that is decimal number. To convert it into corresponding binary number, again we will use repeat division method, in which we will divide the number by 2 and write down the quotient and remainder, and at the end of this process we will write down the remainder from bottom to top. Next is decimal to octal conversion. To convert a decimal number to an octal number, the process will be same as in case of binary number, that is repeat division method, but instead of 2 we will divide the number by 8, because the base of octal number is 8. You can see here, we divide 177 by 8 and find out the quotient and remainder. Again we will divide the quotient, that is 22 by 8. Now the next quotient is 2 and the remainder is 6. Now we will divide 2 by 8, the quotient will be 0 and the remainder will be 2. And we will write this remainder portion from bottom to top direction. Next is decimal to hexadecimal conversion. Again we will use repeat division method, and in case decimal to hexadecimal conversion, we will divide the number by 16, because the base of hexadecimal number is 16. You can see here, we divide the number, that is 378 by 16, the quotient is 23 and the remainder is 10. Now we will divide 23, that is quotient we find in the first step, by 16. Now the quotient is 1 and remainder is 7. Now the next step, we divide the quotient by 16. Now the quotient is 0 and the remainder is 1. Now we will write the remainder portion again from bottom to top direction, that is 1, 7 and 10. As we already discussed that the hexadecimal number system includes digits from 0 to 9 and A to F. That is, to represent 10 we will use A, to represent 11, we will use B. To represent 12, we will use C. To represent 13, we will use D. To represent 14, we will use E. And to represent 15, we will use F. So in this case, we want to represent 10, so we will use A instead of 10 in case of hexadecimal numbers. Next is binary to decimal conversion. As you see, to convert decimal to binary, we divide the number by 2 because the base of binary number system is 2. And to convert the binary to decimal, we will multiply the number by 2. To convert the binary to decimal conversion, firstly write down the binary numbers, then list the power of 2 from right to left. You can see 2 raised to power 0, 2 raised to power 1, then again for 0, 0 raised to power 2, 2 raised to power 3, 2 raised to power 4. Then write the digits of the binary number below their corresponding powers. Then write down the final value of each power of 2, that is 16, 8, 0, 2 and 1. Now connect the digits in the binary number with their corresponding powers and add the final values. So by this process, you will get the final result, that is the decimal number equivalent to binary number. You can see another example, that is 10110101 base 2, that is binary number, and to convert this number into corresponding decimal number, again we will use the same process, that is firstly we will list the power of 2 from right to left, then write the digits of the binary number, then write down the final value of each power of 2, then connect the digits in the binary number with their corresponding powers, and at the end we will add the final values. Next is binary to octal conversion. To find out the binary number for the corresponding octal number, we will take 3 bits of each digit. To convert the binary to its octal number, first of all we will recognize series of binary numbers. Binary numbers are simply strings of zeros and ones, such as 10, 1001, 001 or even just 1. If you see this kind of string, it is usually binary. The next is to group all the ones and zeros in the binary number in the set of 3, starting from the far right. As you can see, we have created this set of 3 digits. Add zeros to the left of the last digit if you don't have enough digits to make a set of 3. As you can see in the second example, in this you don't have enough digits to make a set of 3. So we will add zeros to the left of last digit to make it a set of 3. The binary number, which though not a multiple of 3, can still convert to octal. Just add extra zeros to your front group until it has 3 places. Now you will get the set of 3 digits of a particular binary number, and the next step you have to perform is just write down the corresponding digit. That is, for 010 the digit is 2, so we will write down 2. For 111 the corresponding digit is 7, so we will write down 7. For 100 the corresponding digit is 4, so we will write down 4. In case of binary to octal conversion, we will take only 3 binary digits because the base of octal is 8. If we represent 8 in the power of 2, then it will be represented by 2 raised to power 3. So we will make a set of 3 binary digits. Next is binary to hexadecimal conversion. For binary to hexadecimal conversion, the process is almost same as binary to octal conversion. The only difference is, in case of binary to hexadecimal conversion, we create a set of 4 binary digits, because the base of hexadecimal number is 16 and 16 will be represented by 2 raised to power 4. So in case of binary to hexadecimal number, we will create a set of 4 binary digits. As you can see in this example, we create a set of 4 binary digits from the rightmost side, that is 1011, then 101. You can add zeros to the left of the last digit if you don't have enough digits to make a set of 4. Now in the next example, you can also see we create a set of 4 digits, and you can also add zeros at the left of the last digits if you don't have enough digits to make a set of 3. Then after making the pair, we have to write down the corresponding digit or corresponding alphabet for these 4 digit pair. For example, for 1101, the corresponding digit is D for 1101. So we will write down D. For 101, the digit is 5. So we will write down 5. So by this process, you can get the corresponding hexadecimal number of the binary number. Next is octal to decimal conversion. Octal to decimal conversion is almost same as binary to decimal conversion. That is, by showing each digit place as an increasing power of 8, that is 8 raised to power 0, 8 raised to power 1, 8 raised to power 2, and multiply it with the corresponding digits of the decimal number. And after that, we will find out the addition of these 3 digits, and you will get the corresponding decimal number. To convert a octal to binary, it is very simple process. Converting from octal number to binary is as easy as converting from binary to octal. Simply look up each octal digit to obtain the equivalent group of 3 binary digits. For example, if you want to convert 472 base 8, then simply look up each octal digit, that is 4, 7 and 2 individually, to obtain the equivalent group of 3 binary digits. For example, you can get 100 from this table, 100 for 4, 111 for 7 and 1010 for 1. And by this way, you can get the binary number for the corresponding octal number. Next is hexadecimal to decimal conversion. The conversion of hexadecimal to decimal can also be performed in the conventional mathematical way, that is by showing each digit place as an increasing power of 16, that is 16 raised to power 0 multiplied by 14. 14 is used to represent E in hexadecimal number, then 16 raised to power 1 multiplied by 2, and after multiplying these numbers, we will find the addition of 16 raised to power 1 multiplied by 2 plus 16 raised to power 0 multiplied by 14, and after the addition of these numbers, you will get the final result, that is the decimal number of corresponding hexadecimal number. Next is hexadecimal to binary conversion. Converting from hexadecimal to binary is as easy as converting from binary to hexadecimal. Simply look up each hexadecimal digit to obtain the equivalent group of 4 binary digits. For example, the four binary digits of D is 1101, and the corresponding digits for 5 is 0101. And by this way, you can get the corresponding binary number of 5D base 16. You can see another examples here, that is 39B base 16. We will write the equivalent group of 4 binary digits for B, that is 1011, then for 9, that is 1001, then for 3, that is 0011, and by this way you can get the binary number of corresponding hexadecimal number. Now next is conversion of fractional numbers. For the conversion of integer part, the process is on dividing the quotient of integer part repeatedly by 2 or 8 or 16, whichever be the number system, and separating the remainder till we get 0 as quotient. And for fractional part, on multiplying the fraction repeatedly and separating the integer as you get it till you have all zeros in fraction. Now we will see by one example, that is to convert decimal number 43.125 to binary number. For the integer part, that is 43, we will divide the number, and on dividing the quotient of integer part, that is 43, repeatedly by 2 and separating the remainder. You can see the remainder here, separating the remainder till we get 0 in the quotient. And if we talk about fractional part, that is 0.125, we will multiply the fractional part by 2 because we are converting the decimal number to binary number. We will multiply the fractional part repeatedly by 2 and separating the integer. In case of this number, the integer is 0, and in this number the integer is 0, and in the last one the integer is 1. As you get it till you have all zeros in the fraction. You can see if you separate the integer, that is 1, at the third step, then the remaining fractional number will be 0. So in case of integer portion, the equivalent binary of integer is 101011, because the answer will be read in the direction of this arrow, that is from the bottom to top, that is 101011, and the equivalent binary of fractional part is 001, that is from top to bottom. You will get the fractional part of a number if you read the integer part of the number in the direction of this arrow, that is from the top to bottom. So in this way you can get the binary number of the particular decimal number. If you want to convert the decimal number into octal number, then you have to use 8 instead of 2. If you want to convert decimal number to its corresponding hexadecimal number, then you have to use 16 instead of 2. And the process will be same for converting decimal to binary, decimal to hexa, and decimal to octal. The only difference is the number from which you will divide or multiply the digits. After the conversion of various types of number system, the next step is decimal representation in computers. There exists a way of performing computation in decimal form, but it requires that decimal number should be coded suitably before performing these computations. One such simple representation may be to use first 10 binary combinations to represent the 10 decimal digits, and these are popularly known as BCD, that is binary coded decimal. The binary number system is most natural for computer because of the two stable states of its components. But unfortunately, this is not a very natural system for us as we work with decimal number system. So we use an alternative way of performing computation in decimal form, but it requires that the decimal number should be coded suitably for performing these computations. Normally, the decimal digits are coded in 7 to 8 bits as alphanumeric characters, But for the purpose of arithmetic calculations, the decimal digits are treated as 4-bit binary code. As we all know, 2 binary bits can represent 2 raised to power 2, that is 4 different combinations. Similarly, 3 bits can represent 8 combinations, that is 2 raised to power 3. 4 bits can represent 16 combinations, that is 2 raised to power 4. And to represent decimal digits into binary form, we require 10 combinations. But we need to have a 4-digit code. And one such simple representation may be to use first 10 binary combinations to represent the 10 decimal digits. And these are known as binary coded decimal. You can see the binary coded decimal of the given decimal numbers in the table. That is, for 0 the binary coded decimal is 0. For 1 the BCD number is 0001. For 2, 3, 4, 5, 6, 7, 8, the corresponding number, BCD number is given. For 1, 0, to find out the BCD of 1, 0, we will take the combination of the BCD of 1 and 0 separately. That is for 1, 0001, and for 0, 000 is used. Similarly, for 11, the BCD will be represented by taking the combination of the BCD of 1 and 1 2 times, that is 0001 and 0001, and so on. So this unit provides an in-depth coverage of the data representation in a computer system. This unit covers number system, conversion of number systems, conversion of numbers to a different number system, and decimal representation in computers, etc. So that's all for this unit. Thank you.